Hello everyone, and welcome back to Scrap Paper and Philosophy. And today we start with the question: does wave function in quantum mechanics have a unit? Asked by, let's thank Mr. Halo Abdul Khalak. Halo Abdul Khalak of the University of Sulaimani for asking the question in some corner of the internet, apparently ResearchGate. But first, let's understand the question. So here we have six coordinates, three of space, all in meters, one of time in seconds, and two coordinates of wave function, the real part of the wave function and the imaginary part of the wave function. Well, what are their units, right? So remember, we began with the four elements, two of them obviously dimensions, distance and time, and the other two just amounts of stuff, an amount of mass, an amount of energy, right? Very quantitative, by the way. You can see the units of mass is kilograms. The units of energy are force and distance. So let's take a look at that. Force is newtons, distance is meters. So we have Newton meters. But energy is a little special, too special to be measured in newtons and meters, which are different units, right? Newtons are the units of force, and meters are the units of distance. So we have the joule to measure energy. We have the joule. Let's look at that. Dimensions of energy. So energy is measured in joules, which are defined as dimensions of length squared times inverse square. So meters squared per second squared, I guess. Meters squared per second squared. Meters squared per second. That's very familiar. Meters per second is velocity. Meters squared per second squared is velocity squared. Those are the units of energy. Well, back to this thing here. You know, well, before I'm going to say anything else about this, let me give you my source. Here's if you type. Well, first, let me give you my source. It's this is, I don't remember if it was lecture 2, but this is the class from MIT OpenCourseWare. If you want to know more about quantum mechanics, this is a great source, because you can type MIT OpenCourseWare quantum mechanics, and this is what comes up. It's completely free, MIT OpenCourseWare. And let's see, this is from 2016. So this comes 3 years after I took the class. There's like new classes. I think on MIT OpenCourseWare they have all the old classes. You can like choose which one you want to take. From the University of MIT OpenCourseWare, we're gonna answer the question. Let's see. Well, then we're going to compare with a couple of other answers which are given on on the ResearchGate thingy, which is what you get if you ask the question. That's what that's one of the results that came up when I typed when I typed some version of this question on the internet. This is one of the results that came up, and there's a long involved demonstration with linear algebra that Professor Alan Adams from MIT uh, is going to give on lecture 4 or lecture 5 of his. I don't know, remember which one it was, but it turns out that the dimensions, at least if we're using these coordinates, these 6 coordinates, the dimensions of the wave function are going to be square. Actually, I think that we answer the question of the dimensions of the complex conjugate, which is because, well, let's think about this. I mean, the wave function, right? The wave function f, x, y, z of t equals to a complex number x plus yi. So right there's 2 dimensions, because this is kind of like a fake addition symbol in a sense. I mean, I know it's not fake. I know when you multiply complex numbers together, it does what you would expect in a polynomial sense. If this was an expression like a plus bx. Right. So if this was a plus bx, we have an addition that tells you that you can't mix together. You can't just add the a and the b, because this b has an x on this. Same idea here, but we can take the complex conjugate, which is something which is usually written as this, and it is equal to x plus yi times x minus yi, and that's going to turn out to x squared minus y squared, right? Because there's going to be a plus xyi, a minus xyi, and that's going to cancel, and then there's going to be the other stuff, x squared plus xyi plus xyi, no, plus xyi minus xyi minus, plus y squared I squared, but y squared I squared is just minus y squared. Well, the dimensions of the wave function are, I believe it's 1 over length, and the way which in terms of what I was doing here, length is just distance. Length, distance, we can use these 2 words interchangeably. And 1 over length, if you're thinking in terms of the complex conjugate, it's 1 over length. If you're thinking in terms of individual dimensions, it would be square root of 1 over length. And that's usually regarded as completely meaningless. There's another way to ascribe physical meaning to the wave function, but so they're generally not used. But I want to show you something really interesting. 1 over length equals force, which is measured in Newton, divided by energy, which is measured in Newton meters. If you divide Newton by Newton meters, you're left with meters on the bottom, and that's length. I don't know why the Dr. Adams doesn't tell us this. I even wrote him an email asking him, but he never replied. I guess it's so easy to think about this that it's an insult on his students' intelligence if he was going to even mention it. But this is really, really, really how I would rather think of it. Not as 1 over length, but as force per energy. Well, as we try to keep these videos short, I'm going to save this stuff for next time, and then the time after that I'll get into special relativity, hopefully. Oh, I forgot to show you the answers. The answers, let's see. Well, there's 2 answers here that were given. Let's see. There's this is an answer. This is an answer I actually liked. I like this answer. It comes from Syed Sohaili of Boali Sina University. The dimension of probability density is the inverse of length. Well, I never saw. I mean, the inverse of area. I wasn't aware of this, but he says that it's the inverse of length in one dimension, and then the other stuff. And it's only got 2 recommendations. And then we have a second answer. Well, he actually answers twice. But he says the same thing. Mr. Ulrich Mutze. The answer is simple. The dimension of the wave function is set such that the scalar product in state space is dimensionless, since probability is dimensionless by definition. This gives different dimensions to wave functions in position representation and in momentum representation, and whatever representations you may use. Well, congratulations. 9 recommendations. See? 9 recommendations. Twice. The other one gets 2 recommendations once. So, well, that's it for now. See you later.